Welcome back, guys. In this video, we're going to review all of the convergence and divergence tests for series that we've learned so far. Then we're going to learn a new test, which is called the integral test, and we'll talk about why it works. And then we'll see some examples of this test in action. So let's just start with our review. Remember, if you have a series, it can be written like this. Now we could start with n equals 1, or we could start with any integer. That's our index, and then we go on to infinity. This can be expanded in this way. This is the sum of infinitely many terms. When you substitute in n equals 1, you get a sub 1. Then you add. Then you substitute in n equals 2, and you get a sub 2. And then you add. And you substitute in n equals 3, and then you add. And you keep going forever. The nth term is a sub n, and it goes on indefinitely. Now remember, we say that this series converges if the sequence of partial sums converges. And then remember, partial sums are represented by s sub n. Yes, if the sequence of partial sums diverges, we say the corresponding series diverges. And remember what the partial sums are. S sub 1 is just the first term. It's the first partial sum. Not a lot going on there. S sub 2 is the sum of the first two terms. S sub 3 is the sum of the first three terms. S sub n is the sum of the first n terms. And if we keep going in this way, we're creating a sequence. So it's the first partial sum, the second partial sum, the third partial sum. Eventually we have the nth partial sum. What this paragraph says is, if this sequence of partial sums converges, which means that the limit as n goes to infinity of s sub n equals a number s, which we call the sum of the series. This is a finite number s. That is called the sum of the series, and we'll say that that is equal to this infinite sum. So the sum as n goes from 1 to n, or n goes from 1 to infinity of a sub n, that's the sum of infinitely many terms. It's defined to be the limit of the sequence of partial sums, so we just keep taking a sum of one term, sum of two terms, sum of three terms, sum of n terms, and then we look at how those sums behave. If those sums are approaching a finite number, then we say that that's the sum of the series. If the limit of the sequence of partial sums does not exist, we say the series diverges. Or if it diverges to infinity or diverges to negative infinity, we say the sum of this series, or the series itself that we started with, diverges. So that's the concept. In the last section, we introduced a few series tests. We said if the series is telescoping, we can do the following. And remember, a series is telescoping if its partial sums, s sub n, have a finite number of terms. Well, actually, they all have a finite number of terms, don't they? But it always has pretty much almost always the same number of terms. So maybe for n equals 2 and greater, they're all going to have 2 terms, or they're all going to have 4 terms, or all are going to have 3 terms. But the number of terms doesn't increase as n increases. So we say a series is telescoping if the series, if it's a series whose partial sums have a finite number of terms after cancellation, and these are series that generally look like this. We're going to start with n equals some number and go to infinity. I'm going to just write in 1, but we could start at a different integer. And then we'll have some function of n plus a constant minus a function of n. Or it could be reversed. You could have a function of n over here and a function of n plus a constant over here. But the key is that they're the same function. The only difference between this one and this one is that this one is evaluated at n plus a constant and that one's evaluated at n. They have opposite signs. So as an example of one of these, if I have 1 over n minus 1 over n plus 1, those have the same form. This one's evaluated at n plus 1, this one's evaluated at n. So this is going to be a telescoping series. If I write it out, for n equals 1, n equals 2, n equals 3, and so on, what we have is 1 minus 1/2 when n equals 1, because I've got 1 over 1 plus 1 over 1 plus 1, so that's 1 over 2. When n equals 2, we get 1/2 minus 1/3. When n equals 3, we get 1/3 minus 1/4, and so on. Notice what happens because of the fact that these have the same form. One is positive, one is negative, one is evaluated at n plus an integer, and the other one's just evaluated at n. We get some cancellations. The negative 1/2 and the 1/2 reduce. The negative 1/3 and the 1/3 reduce. The negative 1/4 and the 1/4 in the next term reduce. And so I think the sum of the series is 1. But in order to prove that, we find s sub n, and we take its limit as n goes to infinity. If that sum is, or if that limit is finite, we call that the sum of the series. So that's the telescoping series test. So we find a pattern for s sub n, compute the limit as n goes to infinity of s sub n. So we're determining whether that sequence s sub n converges. If that limit is finite and it equals s, then we say that the series converges to s, or the series equals s, same thing. Okay, so that was the first of our tests. Then we also learned the geometric series test. This is one that we refer back to often. Now the form of a geometric series is this. Now sometimes we've got geometric series that aren't written in this form. But remember, if we substitute in n equals 0 here, we have a times r to the 0. R to the 0 is 1, so that's just a. Then to get to the next term, you multiply by r, and to get to the next term, you multiply by r again, and to get to the next term, you multiply by r again, and that's how that works. Any series that behaves like this, where you start with a number, and to get from term to term, you multiply by the same number, that's geometric. We proved in the last section that this converges under the condition that the absolute value of r is less than 1. So this will converge to, turns out to be the first term over 1 minus r, which is called the common ratio. Provided that the absolute value of r is less than 1. Otherwise, a geometric series will diverge. So I'll just write that on the side. If the absolute value of r is greater than or equal to 1, the geometric series diverges. So if I see a series and it either looks exactly like this, or I notice I've got numbers and numbers raised to powers of n. Possibly plus or minus some other numbers, plus or minus, or multiplied by some other numbers, that's okay. If I can use exponent properties to rewrite the nth term so that it looks like this, it's a geometric series. Or if I expand it and I see that as I'm going from term to term, I'm always multiplying with the same number, it's a geometric series. Now, if that number that I multiply by is a proper fraction, so its absolute value is less than 1, which just means that the proper fraction is just a number between -1 and 1, not including the endpoints. Then this converges, and it converges to a over the first term over 1 minus the common ratio. So we have telescoping series that look like this. We have geometric series that look like this. Let me give you an example of a geometric series. So that's geometric. I know it's geometric because I've got a constant raised to the n. When n equals 0, I get this constant to the 0 power, so that's 1. When n equals 1, I get pi over e. When n equals 2, I get pi over e quantity squared, so that's pi squared over e squared, and so on. So it's geometric. The first term, I identify that to be a, that's 1. The common ratio, it's what we multiply by to get from here to here. I'm multiplying by pi over e, so my common ratio is pi over e. And remember, pi is about 3.14 and e is about 2.7. So 3.14 over 2.7 is definitely greater than 1. So once I've identified a and r, if I want to determine whether a geometric series converges, I just take the absolute value of r. Since the absolute value of r is, greater than 1, because pi over e is greater than 1, the geometric series diverges. Now here's another one that's geometric. It's a little bit less obvious that it's geometric. But notice I've got constants raised to powers that involve n. Since the powers involve n, I can use exponent properties to rewrite this, so it looks like a times r to the n. Or I can just substitute in n equals 1 and see what I get, and substitute in n equals 2 and see what I get. So I'm going to use that approach this time. When I substitute in n equals 1, this is 5 to the 2 minus 3, so 5 to the negative 1, divided by, when n equals 1, I get 3 minus 1 is 2, so that's 3 squared, that's 9. So that simplifies. That 5 goes in the denominator because of our exponent properties. Remember, 1 over x to the n is x to the negative n. So if I have a 5 to the negative 1, that's really 1 over 5 to the first. And we can simplify that, so we get 1 over 45, that's our first term. And then when n equals 2, we get our next term. If we substitute in n equals 2, I've got 2 times 2 is 4, 4 minus 3 is 1, so I've got 5 to the first. When n is 2, I get 3 times 2 is 6, 6 minus 1 is 5, so this is 3 to the 5th. What is 3 to the 5th? 3 times 3 is 9, times 3 is 27, times 3 is 81. So that's 243. So we get 245 over 243 right there. But it's probably more helpful to think of it this way. This is 3 squared. To get from here to here, I'm multiplying by, to get from 5 to the negative 1 to 5 to the first, I have to multiply by 5 squared. And to get from 3 squared to 3 to the 5th, I have to multiply by 3 cubed because there are 3 3's missing. Oops. So my common ratio turns out to be 25 over 27. If I multiply 1 over 45 by 25 over 27, I get 5 over 243. Now, if you work out the answer for n equals 2, or n equals 3, if you find the next term, you'll see that to get from term to term, you're just going to multiply by 5 squared over 27 again, or 25 over 27 again. If you don't believe me, you should work that out for yourself. Now, this is enough information to determine whether the series converges. So I can expand it like this and then identify the first term, identify the common ratio, and then since the absolute value of r is 25 over 27, and that's less than 1, this series converges. And remember, geometric series converge to their first term over 1 minus the common ratio. So we're going to have 1 over 45 over 1 minus 25 over 27. So we'll get 1 over 45, that's 27 over 27, minus 25 over 27 is 2 over 27. And you keep the top fraction and you flip the bottom one and multiply. So 27 is 3 times 9, and 45 is 5 times 9. So we get 3 over 10. So it turns out that this, even though it doesn't look like it, when you add up all of those terms, you get 3 over 10. That's the sum of the series. Okay, so that's how we evaluate geometric series. You could have also used exponent properties for this to rewrite this in a different way to identify A and R. So we've got the telescoping series test. If it looks like this, it's telescoping. We find the pattern for S of n, we compute its limit, and then we compute the sum. Or if we have a series that looks like this, or it can be made to look like this through algebraic manipulation, or alternatively, when I expand it, to get from term to term, I'm always multiplying by the same thing. To get from here to here, I multiply by r. And to get from here to here, I multiply by r. And to get from here to here, I multiply by r. If that's how that works, then it's a geometric series. And if the absolute value of r is less than 1, it turns out that that series will converge to the first term over 1 minus the common ratio. If the absolute value of r is greater than or equal to 1, it turns out that the series diverges. Okay. And then we learned one other test called the Nth Term Test for Divergence. This test cannot tell you whether something converges. That's why it's called the Nth Term Test for Divergence. It says if the nth term of the series goes to 0, and this is not S sub n, it's not the nth partial sum, but the nth term, if that goes to 0, then the corresponding series, or excuse me, if the nth term does not go to 0, the corresponding series diverges. This is a very nice test because after studying sequences a little bit, you probably have some decent intuition at this point for when a limit of some sequence is not 0. Especially when you're looking at a polynomial divided by a polynomial. So for example, if I have the sum as n goes from 2 to infinity of 3n squared minus 1 over 5n squared plus 2, because I've got a second degree polynomial divided by a second degree polynomial, you probably already know the limit of this. It's the same as the equation of the horizontal asymptote if those were x values and this was a function of x. Since these powers of n are the same, we're going to get 3/5. Now technically this, if I'm taking its limit, it's an infinity over infinity indeterminate form. You have to get rid of that problem. But we know, since the powers of n are the same, those are called the degrees of these polynomials in n. Since the degrees are the same, this is going to converge to the ratio of the coefficients. We're going to get 3/5 from this. And 3/5 is not 0. And since 3/5 is not 0, the series diverges. So now I just have to prove this. So you use the nth term test for divergence when you look at a series and you say, it's not telescoping, it doesn't look like two terms that have the same form, one with a positive sign, one with a negative sign, and I can't use algebra to make it look like that. It also is not a constant times a constant to the n, and I can't use algebra to make it look like that, so it's not geometric. But if I look at that nth term, I'm pretty sure it approaches 3/5. That's not 0. So I'm going to use the nth term test for divergence. So I go through my list of all the tests I've learned so far, and I think that doesn't apply, that doesn't apply. Let's try this one. Let's try the nth term test. So we're going to take the limit as n goes to infinity of a sub n, and remember a sub n is this right here. This is the nth term. We're not looking for the nth partial sum, but the nth term. And right now, oops, that's a 5. This is an infinity over infinity indeterminate form. But we're going to do the same thing that we always do. Whenever we have a polynomial divided by a polynomial, we divide the numerator and denominator by the highest power of n in the denominator. And the reason why we do that is when we do that, we end up with a constant plus a bunch of terms that go to 0 in the denominator. And that means everything's going to work out really nicely. It'll be very easy to take the limit. So since the highest power of n down here is n squared, we're going to divide everything by n squared to get rid of the infinity over infinity problem. 3n squared over n squared is a 3. Then we're subtracting 1 over n squared. 5n squared over n squared is a 5. And then we're adding 2 over n squared. And now I don't have the infinity over infinity problem anymore. Now I've got a constant plus this, and as n goes to infinity, this is 2 over a very large number squared. Very large number squared is still large. 2 over a large number is a very small number. So that goes to 0, and that goes to 0, and we get 3/5. Since that limit is not 0, the corresponding series diverges by the nth term test. And again, the reason why it diverges, we talked about in the video over the nth term test, is eventually I'm adding something that's very close to 3/5, so very close to 0.6, to itself infinitely many times. And even though it's only 0.6, 0.6 plus 0.6 plus 0.6 infinitely many times is going to give me infinity. So if this is something other than 0, when I add it to itself infinitely many times, I'm going to get something that definitely doesn't go to a finite sum. It's going to go to positive or negative infinity. So this corresponding series diverges by the nth term test. So you look at this, you take this limit, if you don't get 0, it diverges, and you're done. All right, so that was, we are at 24:05 or so, just a few seconds ago. Now we're going to start talking about the integral test. This is our new test for this section, or this lesson. Here's the integral test. It says, if f of x is positive, continuous, and decreasing Now our book says for all x greater than or equal to 1, but I'm just going to write for all x greater than some particular x. It just has to be eventually decreasing. It has to be decreasing as it goes to infinity. And a sub n is equal to f of n for all n in the domain of the sequence. If that's true, then it turns out that this series, I'm going to write 1 there, but it could start at a different number. This series and this integral, this improper integral, have the same behavior. Now, the value of the index over here and this lower limit are the same. So if the n started at 2 here, I would start my integral at 2 here. So we said this series and this integral, improper integral, have the same behavior. Either both converge or both diverge. So if you have a series and you're trying to determine whether it converges or not, this says, provided that you can replace the n's with x and get this f of x, and this function f is positive, continuous, and decreasing for all x greater than some particular x, then if this integral converges, this series converges. If this integral diverges, this series diverges. I think it's pretty interesting. So let me show you why this is true. So let's say this is our function f. So it's positive, it's continuous, and it's eventually decreasing. After this point, whatever that is, the slope is negative, all the way to negative infinity. If this is what our graph looks like, then this represents the area under the curve, starting at 1 and going to infinity. So maybe this is our graph, and maybe this is x equals 1. And this right here that area of the unbounded region, or unbounded area, is equal to the integral from 1 to infinity of f of x dx. That's how that area is defined. Okay. Now the claim is that somehow this area is related to the convergence of that series. We're going to prove that this series and this integral have the same behavior just using a geometric argument. So let's say I draw some rectangles over here. Let's say I evaluate the function at 1, and then I make a rectangle until I get to x equals 2. And then I evaluate the function at 2, and I make a rectangle until I get to x equals 3. And then I do the same at 3, and the same from 3 to 4, and the same from 4 to 5, and then the same from 5 to 6, and 6 to 7, and so on, just forever. Let's think about what the area of those rectangles is. Well, this is the function evaluated at 1. I want to use another color just so that you can see it a little bit better. The function evaluated at 1, that's f of 1. That's the height of that rectangle. But from up here, f of 1 and a sub 1 are the same thing. So the area of this is actually a sub 1 times 1. So it's just a sub 1. because this is the point on the graph. That's a sub 1. This is a sub 2. This is a sub 3. That's a sub 4. That's a sub 5. That's a sub 6, and so on. So I have just sketched a sub n in purple on this graph. So this area is, the area of the rectangles is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and so on. Okay. Now, because of the way I've drawn this, I've used the left endpoint of every interval and I've evaluated the function there, and I've created a little rectangle. At the beginning, because the function's increasing, this rectangle gives us an underestimate of the area under the curve. It's not quite enough to get that area. But as soon as it starts decreasing, all of these areas of the rectangles are slightly overestimating the area under this curve. Now this one is a little different, but in the limit, like that one little area isn't going to matter that much. It's not going to influence the outcome of whether that integral converges or diverges. Also, getting rid of this a sub 1 here, if I just look at a sub 2 all the way through infinity, starting with n equals 2 to infinity, like that is going to have the same behavior as if I added an extra constant a sub 1 at the beginning. So taking off a constant at the beginning is fine. Now look at all of these guys. How do the areas of this compare to the area under the curve for f? I hope you said it's an overestimate. And if you said it's an overestimate, then you're right. Let's write this down. This shaded region was our unbounded area, and the area of the rectangles here is the sum as n goes from 1 to infinity of a sub n. And because I'm overestimating all the time, and it's not going to balance exactly that one underestimate, this sum, if I'm drawing my rectangles this way, is going to be greater than this, just because I drew my rectangles that way. So what does this prove? Well, I guess this proves that if this integral diverges, since this is a positive function, it's continuous and it's eventually decreasing. If this diverges, it diverges to infinity. Or excuse me. Yes, if it diverges. So I add all of this up, I find this area, and it's infinity. If this is greater than that, well then it has to go to infinity too. So if this integral from 1 to infinity of f of x dx diverges, then this summation also has to diverge to infinity. And that's true because of the relationship between the area of these rectangles and the area under the curve of f of x. Now you can prove this a little bit more rigorously using partial sums, as is done in the textbook, but this is the gist of the argument in the book in that proof. They're just comparing the area of these rectangles to the area under the curve. And so we're able to see that the area of these rectangles is the sum of the series. And if this is infinity, if we add up this area and it's an infinite area, if this is larger than that, well, it has to be infinity too. So keep that in mind. Now the theorem also says either both converge or both diverge. So we just proved that if this diverges, this diverges. Let's prove it the other way too. What if that converges? Let's look at the same picture. Same f of x, and try to draw it the same way. Not bad. Not bad at all. Not great, but not bad. And still, at 1, 2, 3, 4, 5, 6, 7, and so on, if we have what we have here, the points on the sequence are on the graph of f. A sub 1 is there, a sub 2 is there, a sub 3 is there, a sub 4 is there, a sub 5 is here, a sub 6 is here, a sub 7 is here, and so on. So, that should have been more like right there. That's okay. There's my a sub 1. And now I'm comparing, or I want to compare a summation like this to the area under this curve. So we've got unbounded area here, and then if we assume it diverges, so this goes to infinity and this is larger. And if this diverges, then that has to diverge. Now we want to show that if this area is finite, so you evaluate the integral from 1 to infinity of f of x. And this time, let's say you get a finite number, so that this integral converges to that finite number. We want to show that if this integral converges to a finite number, then the summation will also converge to a finite number. One way we can do that is by drawing rectangles as well, but we're going to draw them on the other side. So instead of using the left point of each subinterval, we're going to use the right point of each subinterval. So I'm going to draw a rectangle over here on the interval from 0 to 1 that has a height of a sub 1 and a width of 1. This one has a height of a sub 2 and a width of 1. Height of a sub 3 and a width of 1. Height of a sub 4 and a width of 1. So all these areas are equal to the terms of our series. So there's a sub 7, the next one's a sub 8, wherever that is, and so on. Okay. So now this time, I've got this a sub 1 that's out here. Is not overlapping with the area under the curve from 1 to infinity. And that's okay, because again, one term at the beginning isn't going to make a difference in whether the series converges or not. I'm adding infinitely many numbers over here. If I just add a 7 at the beginning or I don't add a 7, the 7's not going to make a difference. Not for the convergence part. It'll make a difference in the sum, but it won't make a difference in whether the series converges. So now I want to look at the area of these rectangles, at least starting with a sub 2 and going to infinity, and think about how that a sub 2 to infinity, think about how those areas, when I add them all together, compare to the area under the curve. So I've got the integral from 1 to infinity this time, and I want to compare this to the sum as n goes from 2 to infinity of a sub n. Well, notice that first one, that area is an overestimate of the area under the curve, but then because this function is decreasing and because we used our right endpoints, this area a sub 3 is an underestimate of the area under the curve. This one is an underestimate. This one is an underestimate, and so on. So all of these guys are underestimates. So in this case, this sum from n equals 2 to infinity of a sub n is actually less than the integral from 1 to infinity of f of x dx. Does that make sense? Since all of these are underestimates, when I add them all together, the area under the curve is going to be greater. So what does that mean? Well, remember, if this is a finite number, so you evaluate this improper integral and you get 20, and this is smaller. Well, because of the way infinities behave, it's not necessarily going to be less than 20, it's going to be less than or equal to 20. Because of weird things that happen at infinity with the endpoints of those intervals. Okay, so So yeah, if this area, this unbounded area from 1 to infinity is finite, then this is smaller than that, then this has to be finite as well. And then we can tag on that a sub 1 at the beginning. So we have this, and then we add an extra number, and it's still finite. Okay, so what does that say? It says if the integral from 1 to infinity of f of x dx is finite, or we could say if that integral converges, then this is a finite number, which means that series converges as well. And we can start with n equals 1 because we're just adding on a single number at the beginning. Okay. So here's the takeaway. If this integral converges, or excuse me, if the improper integral diverges, the series diverges. If the improper integral converges, the series converges. Now, we have to go back to the statement of our theorem and make sure we understand exactly when it applies. There are a few things that we have to check. It says if the function is positive, so I need to make sure that's true. Continuous, I need to check the conditions for continuous functions and make sure that's true. And it's decreasing eventually, so it's decreasing for all x greater than some x. It's okay if it increases a little bit at the beginning, but if we need it to eventually be decreasing. Provided all those things are true, then I can take the n in this a sub n, replace it with an x, and evaluate this integral. And if this integral converges, this series converges. If this integral diverges, this series diverges. Okay, so that's how it works. Now you can only use this test if those three things are true. And so you have to check, you have to make sure that those three things are true before you use it. And of course, if the series is telescoping, use that test instead. If the series is geometric, use that test instead. If you can tell from the nth term test that the limit of this guy is not 0, use that test. But if you look at a sub n and none of those other tests apply, and you think, I could integrate that. If I replace the n's with x's, I could integrate that. Then you might want to use the integral test. So let's do an example. So let's say we want to use the integral test to determine whether the following series converges. Or diverges. Okay, so the sum as n goes from, let's say, 1 to infinity of n over n squared plus 1. Okay. Now I notice right away that if I replace the n's with x's, I could evaluate the integral of that with a u substitution. So this is a good candidate for the integral test. Also, I know the telescoping series test does not apply because I don't have basically the same function twice evaluated at n and n plus k and a difference of those two functions so that everything will cancel when I write out the summations, when I write out the expanded summation. So it's not telescoping, it's not geometric, I don't see numbers raised to the nth power. And as n goes to infinity, since the degree of the denominator is larger, this is an infinity over infinity indeterminate form, but since the degree of the denominator is larger, as n goes to infinity, a sub n goes to 0. And that's great. That means the series might converge, but it might also diverge. The nth term test is inconclusive. So we have to do something else. So we're going to use our new test, the integral test. Okay, so in order to use the integral test, I need to replace the n's with x's and call that f of x. So let f of x be x over x squared plus 1. Now I need to check three conditions. So first we had to define f of x. Now we need to check the three conditions. Is f positive on the interval from 1 to infinity? Sure, it's positive. And I'm just going to write it out. I'll say f is positive because x is positive when we're on the interval from 1 to infinity. And of course, x squared plus 1 is positive. And that implies that a positive over a positive, that's our f, is also positive. Okay, so f is positive. What's the other thing we had to check? Continuity. F is continuous. Well, remember, all the functions that are defined by equations that we've studied, those are going to be continuous on their domains. So we're looking for three things. We don't want to divide by 0. We don't want to take even roots of negative numbers. We don't want to take a logarithm of a negative number or 0. There are no roots. There are no logarithms. So the only thing we're in danger of doing is possibly dividing by 0. But x squared plus 1 is never 0. I know some students might say, it's plus or minus 1. Close, but not quite. X squared plus 1 equals 0 when x squared equals negative 1. And x squared never equals negative 1, not in the real number system. So this is continuous on the interval from 1 to infinity. So I'm going to say f is well defined. And because it's well defined and it's defined by an equation, it's continuous on the interval from 1 to infinity, so we're good to go there. Because there's no division by 0 and all that jazz. I guess I need to write that down. No division by 0, even roots of negative numbers, or logs of negative numbers or 0. So we check the first two things. The last thing is probably the hardest part to check. We want to check to make sure that this function is decreasing for all x greater than some particular x. So it does not have to be decreasing the whole time. It just has to be decreasing once we get to a certain point. And then we want the slope to be negative after a certain point. Now, in order to check whether that function is decreasing, we can't just take the limit as x goes to infinity. A lot of students want to do that. They say if the limit as x goes to infinity of the function is 0, then the function's obviously approaching 0, and so it's decreasing. Yes, you're right that it's approaching 0 in that case, but it might be oscillating. It might be increasing, decreasing, increasing, decreasing, and then all this goes out the window. We need the slope to be negative, starting at a point and going down. Remember from Calculus 1 how we determined whether the slope was eventually going to be negative? We used what's called the first derivative test. We figured out where the slope was 0 at the top, and then we defined intervals. We just want to show that on the last interval that slope is negative. So that's what we're going to use to show that the function is decreasing. Let me write that down for your notes. So we're using the first derivative test to show that f is eventually decreasing. Oops, sorry, that's off the screen. There we go. All right, and remember, if f is positive, it's going up. If f prime is negative, it's going down. If f prime is 0, you're either at a min or a max, or maybe a flat spot. So we're looking for the function to be decreasing, so we need f prime to be 0 eventually on that last interval. So we're going to, in order to use the first derivative test, the first thing we do is we compute f prime. So f of x was x over x squared plus 1 To compute the derivative, we do the quotient rule. So that's the bottom function times the derivative of the top function. Low d high, remember? Derivative of the top function is 1. Minus high d low, derivative of the bottom function is 2x, all over the bottom function squared. And then we simplify. So I've got x squared plus 1 minus 2x squared. Hey, we've got some like terms. That's a good sign. So this is 1 minus x squared over x squared plus 1, quantity squared. Now if I factor that numerator, that's a 1 minus x and a 1 plus x. So this derivative is 0 whenever the numerator is 0, because I'll have 0 divided by something, and then 0 divided by something is always 0. So the derivative is 0 when 1 minus x or 1 plus x equals 0. So that means x is equal to plus or minus 1. So after we compute f prime, we just set f prime equal to 0 and solve for x. And then you want to create a sign chart. So I've got -1, 1, and I'm interested in the sign of f prime. And actually, I'm not really too concerned about what happens in here. I want to know what happens on that last interval. So f prime is 1 minus x times 1 plus x times x squared plus 1 quantity squared. No matter what interval we're on, if I take x squared plus 1 and I square it, I'm going to get a positive number. No matter what interval we're on, well, and we're not even concerned about these two intervals. When x is greater than 1, 1 plus x is 2. Or excuse me, not 2. When x is greater than 1, say x equals 2, we're going to get 1 plus 2, that's 3. That's positive. When x is greater than 1, say x equals 2, we'll get 1 minus 2, that's -1. So f prime is a negative times a positive divided by a positive. That's going to make it negative. So that means the function is decreasing on the interval, and that's exactly what we wanted. So we determine the sign of f prime on that last interval. And if that sign is negative, we can conclude that the function is decreasing. Okay, I'm running out of time. So I've just proved that my function is decreasing. It's positive, continuous, and decreasing, therefore I can use the integral test. So now I use the integral test. I evaluate the integral from 1 to infinity of x over x squared plus 1 dx. Remember how we do this. It's an improper integral. So the first thing you do is you write it as a limit. The problem happens at the upper limit, so we take the limit as b goes to infinity. We rewrite the integral. Everything stays exactly the same, except you replace that infinity with a b. Then you evaluate the proper integral. So this was improper, but that's proper, so we can use the fundamental theorem of calculus. This particular one requires u sub. I'm going to let u equal the denominator. du is 2x dx, and I've got an x dx up there, so I know it's going to work. I want to get x dx by itself, so I multiply both sides by 1/2. And then I substitute in my bounds to get new bounds for u. So when x equals b, u equals b squared plus 1. When x equals 1, u equals 1 squared plus 1, which is 2. We're still evaluating the integral. So I've got the limit as b goes to infinity of this new integral. New lower bound is 2, new upper bound is b squared plus 1. The x dx turns out to be a 1/2 du. And then what's left is a u in the denominator, so I've got a 1 over u du there. Anti-differentiate. So you have 1/2 natural log of the absolute value of u. Substitute u equals 2 and u equals b squared plus 1 and subtract. If you want, you can factor out the 1/2. I lost my b. It's on the next page. So I've got natural log of b squared plus 1 minus natural log of 2. And then after you've evaluated that integral, and we just did, you compute the limit. As b goes to infinity, remember natural log looks like this. As what's inside goes to infinity, the y values on the graph of natural log of x keep going to infinity. They go very slowly. It's growing very, very slowly. Remember that slope is 1 over x. This is a tiny slope when x is large. If x is 100, that's 1 over 100. It's just crawling to infinity, but it's going to infinity. So as b goes to infinity, b squared plus 1 goes to infinity, so I have natural log of a large number. Natural log of a large number is a large number, so this is going to infinity. Subtracting the natural log of 2 doesn't do much. Taking a large number and multiplying it by 1/2 doesn't do much, so we get infinity. What does that tell you? Well, remember what the theorem said. Provided f is positive, continuous, and decreasing eventually, and a sub n and f of x are basically the same thing. I've just replaced the n's with x's. If this integral converges, the series converges. If this integral diverges, the series diverges. So we just determined that the area under the curve for the integral from 1 to infinity of this function, it has infinite area. That means the integral diverges. Since the integral diverges, I'm going to state my conclusion over here rather than use another sheet of paper. Since the integral diverges, the corresponding series diverges by the integral test. So now you've seen one example of how this is applied. You know where the test comes from. We reviewed the other tests. If the other tests apply, do those. This is the most involved test that you have so far. So you want to use those other tests if they apply. But if you can't use those other tests, they don't apply, and you see something like this, you say, it's not telescoping, it's not geometric, the nth term test doesn't apply, but if I replace the n's with x's, I could integrate that. Just check, is the function positive, continuous, and decreasing? If so, evaluate the integral from 1 to infinity of the function. Then if you get a number, that means the integral converges and therefore the series converges. If you get a limit that does not exist in some way because it's going to positive or negative infinity or something else, then the integral diverges, and that means the series diverges.